My name is James Kelly, and this is my overview of Lab 3, Black Holes and Universal Gravitation. Introduction. The purpose of this lab is to create two computational models that can be first used to define the mass of a black hole given a random trajectory orbit, and second used to test different initial velocities that can allow a theoretical spaceship to escape the gravitational pull of a black hole. Both models are based on computer programs which use universal gravitation formula in different applications in order to test for the various unknowns. The primary physics principles of this lab are velocity, momentum, universal gravitation, net force, change in momentum, parallel versus perpendicular components, and Newton's second law. The main results of this experiment are that, based on the simulations run in two models, the mass of the black hole was found to be 1.34 times 10 to the 34 kilograms, and the initial velocity in order to escape the pull of a black hole is -1 times 10 to the 7 in the x direction, and 9 times 10 to the 6 in the y direction, meters per second. Now I'll go over the main physics principles in more detail. Velocity is a vector quantity describing the change position over time. Momentum is a vector quantity relating velocity and mass. It is described with the equation momentum equals mass times velocity. Universal gravitation is a force that pulls an object in the direction of another object with mass in a vacuum space. The force of gravity between any two objects is found to be negative g m1 m2 over r magnitude of r squared r hat, where g is the universal gravitational constant, m1 and m2 are the masses of both of the two objects, r hat is the direction from the source to the system, and the magnitude of r is simply the distance between the two objects. Net force is the summation of all forces acting on an object, usually expressed as a vector. In this particular experiment, net force is limited to gravity acting on an object from one or two sources. Change of momentum is a quantity that describes the change of an object's speed over time. Parallel and perpendicular components is a method of breaking up net force or change of momentum based on a component acting in the same direction of motion and a component acting in the direction of perpendicular motion. Newton's second law describes how net force affects the change of velocity of an object, and it is characterized by the equation F net equals mass times change of velocity over change of time. This can be arranged to several different derivations, such as the position or velocity update formula. Conditions of the experiment. The initial condition is set in space with a black hole at the origin and either a star or a planet with a spaceship on it orbiting the black hole. The initial time is 0, and the system is the first model. In the first model is the star, and in the second it is the spaceship. The surroundings are just the black hole in the first model and the black hole and the planet in the second model. For both computational models, it is assumed that gravity from the black hole and planet are the only sources of force affecting the system. These assumptions are made in order to simplify the net force acting on the system. Because the system experiment is situated in space, technically there should be infinite sources of gravitational pull on the system, but these are simplified. Part 1 was to find the mass of the black hole. The first computational model produces a random trajectory of a star orbiting a black hole. This trajectory was generated based on inputting a Georgia Tech email address. The objective was to use the trajectory and motion of the star in order to predict the mass of the black hole. This was done by reverse engineering the net force by using the change in position and change in velocity. By knowing the net force, it is possible to calculate the mass of the black hole because the mass of the star was given to be 2 times 10 to the 30 kilograms. The mass of the black hole was calculated with the universal gravitation formula during each iteration, and these results were averaged to get a final mass of 1.342 times 10 to the 34 kilograms. The primary concept used to obtain net force was splitting the force into its parallel and perpendicular components. The final mass was calculated with the universal gravitation formula. So on the code here, you can see that the actual momentum in the parallel direction was able to be found with the change in magnitude of the change in momentum over change in time, and then this was then subtracted from net force in order to find the perpendicular. The next part was to find the escape velocity. The next scenario presented in the experiment was a spaceship on a planet which was attempting to leave the planet, which was orbiting the same black hole from part 1. The objective of the second model was to find a velocity which would allow the spaceship to escape the orbit of the black hole while still being somewhat close enough to observe it. To accomplish this, the net force was repeatedly calculated based on the universal gravitational formula. The effect of gravity on the spaceship needed to be calculated from two sources, the black hole itself and the planet. Net force needed to be repeatedly calculated because the distance between the system and the sources of gravity were constantly changing. After the new net force was calculated at each iteration, Newton's second law was applied to find the change in position, and then the change of velocity, and then the change in position. There are technically infinite velocities which satisfy the objective. However, the velocity used in the model was -1 e7 in the x direction, 9 e6 in the y direction, meters per second. Discussion. Comparison between models. The two models are extremely similar, containing a black hole at the origin with various gravitational forces. The main difference between the models come from the observed system and what the unknown the program is used to find. Sources of error. One source of error in both models is the limiting of the surroundings to only the black hole or the black hole and planet. Because there are other objects in space, no matter how far away they are technically influencing the net force in the system, which both models do not account for. This means that the computational models cannot be considered perfect predictions of movement, although they are extremely close because the effect of these other objects are very tiny. Conclusions. What does it mean? What is the difference between the net force and the change of momentum? Well, initially it may be inferred that these values mean the exact same thing because of their similarities. However, this is not the case. In reality, they refer to different things, as net force is a quantity specifically about how an object is affected by other things, aka forces. Change of momentum, on the other hand, is simply a way to characterize how an object moves over time. Further, their perpendicular and parallel components follow the same distinction, with forces acting on the object in a particular direction versus how an object moves in a particular direction. Essentially, there are two distinct concepts. They just happen to have the same quantity. What if the objective in the second model was to find a velocity which puts the spaceship into an orbit around the black hole? Because the spaceship starts with a y coordinate of 0, you can simply apply a velocity in the y direction and set the x velocity to 0. And the net force iterations will adjust it from there. The only limit is that the velocity needs to be large enough so that it outpaces the velocity of the planet for the first few instances. The initial velocity used was 9.9 e to the 6, 0.